Discover how raw aluminum and steel are transformed into powerful machines through precision metalworking, forging, and assembly. The recycling process begins with the collection of scrap materials from demolished buildings and construction sites. When buildings are dismantled, steel beams, pipes, and various metal components are carefully separated from concrete and other non-metal materials. The steel scrap is transported by truck to the Takunin recycling plant, where it undergoes the first stage of inspection. Upon arrival at the facility, the scrap is unloaded onto sorting yards. Skilled workers and automated machines classify the steel according to type, size, and contamination level. This step is crucial, as separating clean ferrous metals from mixed or coated materials ensures that the recycling process runs efficiently. After the initial sorting, magnetic separators are used to remove non-ferrous impurities and isolate pure iron and steel components. After sorting, the scrap is subjected to a detailed inspection process. The plant's quality control team examines the material to detect any hazardous or unsuitable items, such as sealed containers, gas cylinders, or chemical residues that could cause explosions or contamination during melting. Once the inspection is complete, the acceptable steel pieces are fed into a pre-processing line equipped with shearing and crushing machines. Large steel beams or frames are cut into smaller, manageable pieces, usually around 30 centimeters in length. This size reduction facilitates easier handling and uniform feeding into the melting furnaces used by steel makers later in the chain. The plant can process up to 5,000 tons of scrap per month, reflecting its high operational efficiency and capacity to support regional recycling efforts. One of Takunin's most important recycling operations involves ELV recycling, referred to in Japan as. According to Japan's automobile recycling law, car owners pay a recycling fee at the time of purchase, which is later used to safely process the vehicle once it reaches the end of its life cycle. The process is carefully regulated to ensure environmental safety and efficient material recovery. The first step in ELV recycling is the recovery of fluorocarbon gases from the vehicle's air conditioning system. These gases, commonly known as freon, contribute to global warming and ozone depletion if released into the atmosphere. Using specialized attachments and vacuum recovery units, trained technicians extract the refrigerant gas from each vehicle and store it securely in pressurized cylinders for proper disposal. Next, technicians remove hazardous components such as batteries, motors, and pyrotechnic devices like airbags and flares. Batteries contain lead plates that are later sent to certified secondary smelters for lead recovery. Airbags, which contain explosive charges, must be safely neutralized before dismantling to prevent accidental deployment. Other potentially dangerous materials, such as flare sticks or small gas cartridges, are also carefully removed. Once these safety steps are completed, workers remove tires, glass, plastic parts, and interior materials asterisks for separate recycling or disposal. Tire balancing weights, which often contain lead, are also removed to prevent contamination in the steel recycling stage. Only the remaining metallic vehicle body composed primarily of steel is sent forward for shredding and smelting. The stripped vehicle shells and other steel scrap are then fed into a large shredder. This powerful machine tears the metal into small fragments, allowing efficient separation of materials. Magnetic systems attract and collect ferrous metals, while non-magnetic materials such as aluminum, copper, and plastic are sorted out using air classifiers or eddy current separators. The recovered steel fragments are cleaned and compressed into dense cubes or briquettes to facilitate transportation. At Takunen's facility, specialized loaders and conveyor systems move the processed scrap to storage areas. From there, it is transported to steel mills, where it becomes the feedstock for electric arc furnaces. In these furnaces, the recycled steel is melted down and refined into new products, such as construction beams, reinforcing bars, or automotive steel sheets. This closed-loop system significantly reduces the demand for virgin iron ore and helps cut carbon emissions associated with mining and raw steel production. The Takunen Group's recycling system exemplifies Japan's commitment to sustainability and circular resource management. By recovering metal from both demolition waste and ELVs, the company contributes to a substantial reduction in landfill use and greenhouse gas emissions. Moreover, the energy required to melt recycled steel is only a fraction of that needed to produce steel from iron ore, which makes recycling both environmentally and economically beneficial. The recovered materials are also vital to Japan's domestic steel industry, which relies heavily on high-quality scrap as a raw input. Takunen ensures consistent supply through strict quality control, advanced sorting technology, and adherence to all safety and environmental standards. The steel recycling process at Takunen Group is a model of modern resource recovery and environmental stewardship. From collecting demolition scrap and dismantling vehicles, to safely recovering hazardous substances and producing reusable metal, every step of the process reflects precision, efficiency, and sustainability. The traditional yet highly precise process of forging a steel shaft at Dero Stahl in Remscheid, Germany. This process takes place on a massive 3,000-ton hydraulic press, where a steel billet is gradually shaped into a strong, durable shaft through controlled pressure and heat. This sequence highlights both the power of industrial forging technology and the skill of experienced craftsmen who ensure the metal achieves the required structure and geometry. The process begins with the preparation of the raw billet. A solid steel block or cylindrical piece, known as the rolling, is selected according to the desired size and material specification of the final shaft. The billet is then heated in a furnace to a temperature of approximately 200 degrees Celsius, which makes the steel malleable enough for forging while maintaining its internal integrity. The glowing billet is transported from the furnace using heavy-duty tongs or a manipulator, and positioned carefully under the forging press. Once in place, the hydraulic forging press, with an enormous capacity of 3,000 tons of force, gradually compresses the billet between massive dies. Each press stroke reduces the billet's cross-section and elongates its length, transforming it step by step into the rough shape of a shaft. The operators precisely control the pressure and stroke to ensure uniform deformation. This stage is critical as it refines the metal's grain structure, eliminating internal voids and enhancing the mechanical strength of the steel. Throughout the forging process, temperature control is vital. After each pressing cycle, the billet may be reheated to maintain its plasticity. Skilled operators constantly monitor its color and temperature to avoid overcooling or overheating, both of which could compromise the steel's quality. The combination of repeated pressing, reheating, and turning ensures that the shaft is symmetrically formed and free from internal defects. After the main forging is completed, the semi-finished shaft is trimmed and straightened. Excess material, such as flash or uneven ends, is removed using shears or cutting torches. The shaft is then returned to the press for final shaping, giving it the precise diameter and contour required for its intended use. In some cases, a hammer press or manipulator may assist in refining the transitions and shoulders of the shaft, achieving a near-net shape before machining. Once forging is complete, the shaft undergoes controlled cooling in the air or in a furnace to relieve internal stresses. This is often followed by heat treatment processes such as normalizing, quenching, and tempering, which further enhance toughness, hardness, and fatigue resistance. These steps are essential for shafts that will later serve in demanding applications like turbines, gearboxes, or heavy-duty machinery. Next, the forged blank is transferred to the machining department, where it will be turned, milled, and ground to exact dimensions. The forging process provides a dense and oriented grain structure that gives the final part exceptional strength compared to a cast or welded component. The superior mechanical properties achieved through forging are particularly important in applications requiring high torque, bending resistance, and long service life. Finally, each shaft undergoes inspection and quality control. Non-destructive testing methods such as ultrasonic or magnetic particle inspection ensure the absence of internal cracks or inclusions. Dimensional checks confirm that the forging meets the customer's specifications before it proceeds to final machining or assembly. In summary, the forging of a steel shaft at Die Rostall Remscheid demonstrates the synergy between advanced hydraulic technology and human expertise. Using a 3,000-ton hydraulic press, the company transforms a simple billet into a high-performance component with superior structural integrity. The process not only shapes the metal but also strengthens it from within, embodying the enduring craftsmanship and precision that define German steel forging. The hot rolling process of the 150mm steel plate begins with heating the plate to a high temperature until it becomes malleable. The softened plate is then fed between 3 adjustable rollers of the plate rolling machine. The 2 bottom rolls move independently to control pressure and curvature, while the top roll moves vertically to form the desired bend. Through several passes, the plate is gradually shaped into a cylindrical or conical form with high accuracy and uniform thickness. The symmetrical roller arrangement ensures even force distribution and minimal flat ends. Finally, the rolled plate is released for cooling and further processing. The aluminum extrusion manufacturing process begins with premium raw materials sourced from international melting plants, where the quality of each billet is strictly guaranteed. These billets are first processed in a 16-inch billet cutting machine, which cuts them to the required lengths. Next, they are heated uniformly in a 16-inch billet preheating furnace, while the corresponding molds are simultaneously warmed in a mold preheating furnace to maintain optimal extrusion conditions. Once the billet reaches the correct temperature, it is transferred to a 6,000-ton seamless and SEMI extruding machine, which forces the hot aluminum through a die to produce profiles with a cross-section of up to 500 millimeters. The extruded aluminum, still hot and slightly deformed, is immediately stretched on a 450-ton stretching machine to remove internal stresses and ensure perfect straightness. The profiles are then aged in a 13.5-meter aging heat-treating furnace, which strengthens the material and enhances its hardness and durability. After heat treatment, the products undergo precise straightening by a multi-axle straightening machine to guarantee exact size and alignment. They are then cut to length using a 45 degrees double-blade angular sawing machine and an electric automatic cutting machine, ensuring accurate dimensions, smooth surfaces, and clean edges. The company operates its own anodizing plant, where extrusions up to 6 meters long are anodized for corrosion resistance and visual appeal. In addition, various surface finishes such as liquid, powder, and fluorocarbon painting are available for profiles up to 10 meters long, meeting diverse customer needs. Every stage of production is supported by rigorous quality control. The facility employs a universal materials testing machine for strength testing, Webster and Barkle hardness testers for surface hardness evaluation, and flatness measuring instruments for precise dimensional checks. Advanced 3D and 2D image measuring instruments are also used to verify accuracy and consistency. Environmental responsibility is a key principle of the company. It operates its own wastewater treatment plant to minimize environmental impact and promote sustainable production. Combining professional equipment, integrated manufacturing, fast delivery, and strict inspection standards, the plant ensures high-precision aluminum extrusions that meet international quality and environmental protection requirements. The Komatsu P23MN extrusion line is a high-performance aluminum extrusion system designed and manufactured by Komatsu Solutions, a company well known for its advanced extrusion technologies. This line represents a complete and often fully automatic solution for producing long, continuous aluminum profiles used in a wide range of industrial applications such as construction, automotive, and electronics. The P23MN is offered in different configurations, including models that process 7-inch and 8-inch billets, providing flexibility for various production needs and output capacities. The extrusion process begins with solid aluminum billets, sourced from quality-controlled melting plants. These billets are first preheated to the required extrusion temperature, ensuring optimal material flow. Once heated, the billets are transferred to the press zone, where a powerful hydraulic press forces the softened aluminum through a precision-engineered die. This die shapes the metal into continuous profiles with specific cross-sectional geometries. The pressure and temperature are carefully controlled to ensure dimensional accuracy, surface finish, and mechanical strength. After extrusion, the long aluminum profiles move along the runout table for controlled cooling, usually by air or water. The cooled profiles are then stretched to remove internal stresses and to achieve the correct straightness. Following this, they are cut to length using automatic saws and transferred to aging ovens, where a heat treatment process enhances their mechanical properties and stability. A key advantage of the Komatsu P23MN line is its automation. From billet loading to final product stacking, the system can be fully integrated and computer-controlled, reducing labor costs and improving production consistency. The line is also equipped with safety systems, energy-efficient drives, and easy-to-use operator interfaces, ensuring reliable and sustainable operation. Designed for companies aiming to upgrade or replace existing extrusion equipment, the Komatsu P23MN combines advanced engineering with user-oriented functionality. It guarantees high productivity, excellent product quality, and long-term reliability, making it a preferred choice in modern aluminum extrusion manufacturing. The welding of trailer chassis is a crucial process in ensuring the strength and durability of heavy-duty transport vehicles. At Turbos Hoet in Belgium, an advanced arc welding robot solution has been implemented to improve both quality and efficiency in chassis production. The installation features a Panasonic TL200WGH3 welding robot designed specifically for precision and reliability in automated welding applications. This robot is mounted on a gantry system that moves along a 16-meter track, allowing it to cover the entire length of the trailer chassis with smooth and accurate movements. The gantry design enables the robot to reach multiple welding positions and perform continuous welds on large and complex structures without manual repositioning. To ensure welding accuracy, the system is equipped with quick touch sensing, a technology that checks and adjusts the robot's program before and during welding. This feature allows the robot to detect deviations in joint positions and automatically correct its path, ensuring consistent weld quality even in case of slight misalignments or part tolerances. The DTPS offline programming software is used for programming the robot. This powerful tool allows engineers to create, test, and optimize welding programs on a computer before applying them to the actual machine. As a result, downtime on the production line is minimized, and setup time is significantly reduced. Overall, the combination of advanced robotics, intelligent sensing, and precise programming results in a highly automated welding solution. It not only guarantees uniform welds and structural integrity, but also enhances productivity, safety, and cost efficiency in the manufacturing of complete trailer chassis. The spool-based pipeline fabrication process begins when each pipe is rolled into the pipe-facing station. Here, the pipe end is cleaned both inside and outside to remove any contaminants. The pipe end is then beveled to prepare for automatic welding, ensuring the correct edge geometry. An inspector checks the offset and land to confirm accuracy. Once approved, the beveled pipe is transferred to the preheat station. In this station, the pipe end is buffed to establish a good welding ground, and magnetism testing is performed. The band is aligned, and induction coils are placed around the pipe ends to preheat them to the specified temperature. When preheating is complete, welding begins. The reach rod is inserted into the upstream pipe, and the internal clamp is pulled into position. The rear shoes are set, and the next pipe joint is aligned. The spacer checks the fit by tapping the joint, signaling readiness. The reach rod operator raises the clamp's front shoes, and P450 CMT welding bugs are mounted on the band. The torch tip is aligned precisely, and the CMT root pass is deposited. As the root pass is completed, other welding stations perform their passes in sequence, maintaining a continuous process. The hot pass and first fill are then deposited using P625S units, followed by the second and final fills. Finally, the cap pass is applied to complete the weld. The finished weld is dressed, and all spatter and silica are brushed away. The cap pass is visually inspected to ensure surface quality. Next comes non-destructive testing. The weld undergoes automated ultrasonic testing, which provides immediate scan results. After inspection, the joint enters the closed-cycle abrasive blasting stage. Here, abrasive material is blasted at high speed to remove oxidation and surface contaminants, while a vacuum immediately recovers the abrasive. The coating process follows. Using an induction coil, the weld area is heated to the application temperature. The fusion-bonded epoxy coating head is positioned on the pipe, and coating begins as the head rotates. Finally, injection-molded polypropylene coating is applied. The extruder deposits molten polypropylene, while radiant heat prepares the factory coating for bonding. The mold is aligned with a laser, locked hydraulically, and filled from the bottom with polypropylene. After cooling, the mold is opened, excess material is trimmed while still soft, and the joint is quenched to complete the process. The Komatsu UK factory features a modern and highly efficient assembly line dedicated to building hydraulic excavators. This moving line, stretching 156 meters in length, represents the heart of the plant's production system. Operating at a steady pace of 200 millimeters per minute, it allows approximately 37 minutes of working time at each station, ensuring both precision and consistency in assembly. The process begins with the construction of the main structural parts, including the booms and the revolving frame. As the frame moves along the line, key components such as the engine, fuel and hydraulic tanks, and the operator's cab are carefully installed. After these main assemblies are fitted, the completed upper structure is mounted onto the track frame, forming the core of the excavator. Throughout the process, cranes play a vital role in lifting and positioning large or heavy components, assisting the main assembly team in maintaining a smooth and continuous workflow. Meanwhile, certain sub-assemblies are prepared on the sidelines to ensure a steady supply of ready-to-install parts. The moving assembly line design ensures a synchronized and ergonomic working environment where each operator performs specific tasks within a controlled time cycle. This system not only increases production efficiency, but also maintains the high-quality standards that Komatsu is known for worldwide. Overall, the Komatsu UK assembly line exemplifies advanced manufacturing technology and precision engineering in modern heavy equipment production.